In this problem, we've got a given matrix, and we're trying to do two different things. Solve this difference equation, and, well, not completely solve the differential equation, but at least sketch its vector field and try to draw some solution curves. All right, the difference equation, technically, you don't need calculus for. You could teach this to people who don't know any calculus. How do you solve this? It's analogous to what we did with scalar equations. And this is something I talk about in the lectures. It's effectively, you iterate this by doing what? By replacing xn minus 1 with a times xn minus 2. And then you keep going. Well, and use the associative property. And yes, this is a squared. A times a is called a squared. Use the recursive equation again. Replace xn minus 2 with a times xn minus 3. And that's the same as a cubed times xn minus 3. And now you see the pattern. You imagine, keep going here until you get a to some power times x0, the initial condition. What's the power of a? Well, notice the power of a is what you subtract from the n. So to get a subscript of 0, you need to subtract n from n minus n. This has got to be a to the nth power. But this does beg a question. How do you find a to the nth power? Right? This is definitely true and relatively easy to see here in the abstract. But how do we find a to the nth power? For a general matrix, it's a pretty hard thing, actually. That's one of our main topics in about lectures 20 through 26 or so, like 5 or 6 lectures. We talk about finding a to the n power. I might get the lecture numbers wrong there. Something like 4 or 5 or 6 lectures for the linear algebra part are focused on that. However, for special matrices, it's not too hard to do, and that's what I do in lecture 14. This is a special matrix, though you got to recognize it. It is a rotation matrix for some angle. There is some angle theta such that these two matrices are the same. What angle theta? How about pi over 2? 90 degrees. Cosine of pi over 2. Cosine of 90 degrees is 0. Sine of pi over 2, sine of 90 degrees is 1. And yeah, there we have a negative sine of 90 degrees and cosine of 90 degrees. Theta is pi over 2 radians, 90 degrees. And in the lecture, using some trigonometric identities, effectively, I don't fully prove it, but effectively we see that in this case, when you've got this rotation matrix, that it turns out that a to the nth power is cos of n theta negative sine of n theta, sine n theta, cos n theta. And x0 we took to be 1, 1. Theta again is pi over 2. So technically speaking, one way to write the answer is cosine of n pi over 2, negative sine of n pi over 2, sine of n pi over 2, cos of n pi over 2 times the vector 1, 1. And yes, you could do that multiplication as well. And oh, I'm being inconsistent. I'm using parentheses there and square brackets there. It doesn't matter. Do a linear combination of these columns. I mean, you can write it as just a single vector, but you also could write it as a linear combination. Effectively, 1 times the first column plus 1 times the second column. You can write the answer in this way if you like. And again, you could combine these into one vector if you want as well. Though it's nice to write these things as linear combinations because that's going to generalize. And you could even simplify that for different values of n, depending on whether n is A multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, 3 more than a multiple of 4. Cosine of n pi over 2, if n is a multiple of 4, turns out to be 1, and sine of n pi over 2 turns out to be 0 if n is a multiple of 4. I won't write down the rest. If n is 1 more than a multiple of 4, like 1 or 5 or 9 or 13, then that one's 0 and that one's 1. You're at an angle equivalent to 90 degrees. If n is 2 more than a multiple of 4, like 2, 6, 10, 14, then the cosine's -1 and the sine's is back to 0, because the angle really is equivalent to 180 degrees. And if n is 3 more than a multiple of 4, like 3, 7, 11, 15, then I think this one ends up being 0 and this one ends up being -1. You're 270 degrees. Yeah, this does correspond to rotations. It is a rotation. Geometrically, what's happening here is applying this recursive equation is taking your given vector and always rotating it by 90 degrees every iteration. What about the vector field for the corresponding system of differential equations? In scalar form, this is dx dt is -y, dy dt is x. The right-hand sides here define something you can call a vector field. Capital F of capital vector y, vector F of vector y, has output -yx. What in the world is this about, and how can I possibly graph it? You imagine the inputs as being points. In fact, you might prefer writing this as f of the point xy. That's okay. It's inconsistent notation, but it's beneficial notation. You think of the inputs to a vector field as being points, and you think of the outputs as being vectors that are drawn as arrows and could be written with I hat, j hat notation if you like, -y I hat plus x j hat. At each point in the plane, you draw this vector. Now, of course, nobody can literally do that at every point in the plane because that's infinitely many points, and not even computers can do that. But let's draw a few and see if we get a feel for what the vector field looks like. So you've written that down. Let's go ahead and do it on another piece of paper here. Guess I'll rewrite it up here. So there's our vector field. For example, what is the output of the vector field at the input 1, 1? It's the vector -1, 1. At the point 1, 1, you'd want to draw an arrow with these components. -1, +1, so it'd have to look like this. This is 1 here, this is 1 here, this would be 2. F of 1, 0 is 0, 1. At this point, 1, 0, you'd want to draw a vector, unit vector pointing straight up. F of 0 to 1, to pick another point, is -1, 0. I'm just using this formula. Here, x is 0, y is 1. Use the formula, get this vector. At 0, 1, we plot this vector that points directly to the left and is a unit vector. Are we always going to get a unit vector? No. In fact, this one's not a unit vector. F of 0, 2, for example, is -2, 0. At this point, I'd want to draw a vector pointing to the left, but twice as long as this one. If you plot more of these, what kind of thing will you see? You'll see some sort of rotation going on here. Well, is that because it's a rotation matrix? Yeah, Okay, I'm not being very careful here. And that means, what do solutions of the system of differential equations do? This system, just like with slope fields, they follow, in this case, the vector field. But it's more than just being tangent to them. They also have to travel in the direction of the vectors. You need to draw these with arrowheads. The direction is important. They're really parametric curves, as in multivariable calculus parametric curves, that follow the vector field. And so, do they end up being circles here? They actually do. They end up being circles centered at the origin, with the circles being traversed counterclockwise as t increases. So you draw the arrows going counterclockwise. What kinds of functions would give you solution curves that look like this? Oscillating, really. Imagine moving around these curves over and over again. How about trig functions? I wonder if x equaling cosine of t and y equaling sine of t solves the system. I think it does. If x is cos t and y is sine t, dx dt is the derivative of cos t is negative sine t, which is also the same as negative y. And dy dt would be cos t, which is also the same as x. It works. Those two parametric equations, as in multivariable calculus, parametric equations solve, as one object, solve the system of equations. This one parametric curve solves the system of equations. It's a solution of the system. You didn't have to know that, but I wanted you to draw the vector field instead. The emphasis in section 2.2 is on the vector field idea.